Throughout modern history, certain machines have grown so vast in scale and ambition that their costs rivaled the economies of entire nations. These projects were not measured in millions, but in decades, political will, and sustained national funding. They demanded massive workforces, specialized industries, and long-term commitments that reshaped budgets and priorities far beyond their original scope. Built to project power, explore space, generate energy, or unlock fundamental knowledge, these machines often became symbols of both achievement and excess. Their stories reveal how engineering brilliance, strategic pressure, and prestige can drive costs to extraordinary heights, forcing governments to confront the true price of technological dominance. The International Space Station, the most expensive machine ever assembled. The International Space Station, commonly known as the ISS, is the most complex and expensive machine ever constructed by humanity. Its origins date back to the early 1980s when the United States proposed Space Station Freedom as a permanently crewed orbital laboratory. Following the end of the Cold War, the project was restructured in 1993 to include Russia, Europe, Japan, and Canada, transforming it into a multinational effort intended to share costs, expertise, and political responsibility. The first module, the Russian-built Zarya, was launched in 1998, marking the beginning of continuous on-orbit assembly. Construction of the ISS spanned more than a decade, requiring over 40 assembly missions using the Space Shuttle and Russian Proton and Soyuz rockets. Major contributors included NASA, Roscosmos, the European Space Agency, JAXA, and the Canadian Space Agency. The station ultimately grew to a mass exceeding 420 metric tons, with a pressurized volume comparable to a 5-bedroom house and solar arrays spanning more than 100 meters. Every component had to be designed to survive launch, vacuum, radiation, and extreme temperature swings while remaining serviceable by astronauts in orbit. The financial scale of the ISS is unmatched. Total life cycle costs, including development, launch, assembly, operations, and maintenance, are estimated to exceed $150 billion. NASA alone spent over $100 billion by the early 2000s, with partner nations contributing tens of billions more. At its peak, the annual operating cost rivaled the entire national budgets of smaller countries. This immense expenditure made the ISS not just a scientific platform, but a long-term geopolitical commitment that few governments could easily abandon. Technically, the ISS functions as a microgravity laboratory, supporting research in physics, biology, medicine, materials science, and Earth observation. It has hosted continuous human presence since November 2000, making it one of the longest-running crewed projects in history. However, critics have long argued that its scientific output does not fully justify its cost, especially when compared to robotic missions that achieve results at a fraction of the price. The station's complexity also created long-term dependency. Specialized modules, life support systems, power distribution networks, and international logistics chains made the ISS extremely difficult to decommission or replace. Political tensions between partner nations periodically threatened cooperation, yet the station continued operating because shutting it down prematurely would waste decades of investment. Today, the ISS stands as both a triumph and a cautionary tale. It proved that rival nations could build and operate a single machine in orbit, but it also demonstrated how large-scale projects can grow beyond original intentions and budgets. The International Space Station was not abandoned, but its cost ensured that nothing of comparable scale is likely to be attempted again anytime soon. The B-2 Spirit stealth bomber, one aircraft priced like a national economy. The Northrop Grumman B-2 Spirit is one of the most expensive and technologically ambitious military aircraft ever built, to the point where each individual bomber rivaled the economic output of small nations. The program originated in the late 1970s, when the United States sought a next-generation strategic bomber capable of penetrating increasingly sophisticated Soviet air defenses. Building on earlier flying wing research, including the YB-49, Northrop was selected to develop a stealth aircraft that relied on low observability rather than speed or altitude for survivability. The B-2 first flew on July 17, 1989, and entered operational service in 1997. Its distinctive flying wing configuration, radar-absorbing materials, and precisely controlled surface geometry dramatically reduced its radar cross-section. Unlike earlier bombers, the B-2 was designed from the outset to evade detection by radar, infrared sensors, and acoustic tracking systems. This capability allowed it to strike heavily defended targets without escort, a revolutionary concept at the time. What truly set the B-2 apart, however, was its cost. Originally, the U.S. Air Force planned to acquire 132 aircraft. As the Cold War ended and defense budgets tightened, that number was steadily reduced. Ultimately, only 21 B-2 bombers were built between 1987 to 2000. The massive reduction in production caused per-unit costs to skyrocket. Including research, development, testing, and procurement, the average cost per aircraft exceeded $2 billion. Adjusted for inflation, that figure rivals or exceeds the annual gross domestic product of several small countries during the same period. The aircraft's complexity drove these costs even higher over its service life. The B-2 requires climate-controlled hangars to preserve its stealth coatings, extensive maintenance hours per flight hour, and highly specialized training for both aircrew and ground personnel. Even routine operations involve enormous logistical and financial investment. Operating costs per flight hour are significantly higher than those of the B-52 or B-1B, despite the much smaller fleet size. Despite its expense, the B-2 proved operationally effective. It conducted its first combat missions in 1999 during the Kosovo conflict, flying directly from the continental United States to strike targets in Serbia. It later saw action in Afghanistan, Iraq, and Libya, delivering both conventional and nuclear-capable precision weapons with high reliability. Its ability to operate globally without forward basing justified its strategic value in U.S. defense planning. The B-2 Spirit was never abandoned, but it was effectively capped by its own cost. The aircraft became too expensive to expand, upgrade rapidly, or replicate. Instead, it served as a technological bridge to later designs, such as the B-21 Raider. The B-2 stands as a rare example of a weapon system so advanced and so costly that a single airframe represented an investment on the scale of a national economy. The Gerald R. Ford class aircraft carrier, a warship with a national-level budget. The Gerald R. Ford class aircraft carrier represents the most expensive warship program ever undertaken by the United States Navy, redefining both the scale and cost of modern naval power. Conceived during the late 1990s as a replacement for the aging Nimitz class, the program was intended to incorporate revolutionary technologies that would reduce crew size, increase sortie generation, and extend service life. The lead ship, USS Gerald R. Ford, CVN-78, was laid down in 2005 and commissioned in 2017 after years of delays and cost growth. At its core, the Ford class was designed to be a generational leap rather than an incremental upgrade. The most significant change was the introduction of the A-1B nuclear reactor, which generates substantially more electrical power than previous designs. This increased capacity was meant to support future systems such as advanced sensors, electronic warfare suites, and directed energy weapons. The class also introduced the electromagnetic aircraft launch system and advanced arresting gear, replacing steam catapults and hydraulic arresting systems used since the 1950s. These technological ambitions came at an extraordinary cost. The USS Gerald R. Ford alone exceeded $13 billion in construction costs, while total program expenses, including research and development, pushed the figure far higher. Each subsequent ship remains among the most expensive naval assets ever built, with budgets comparable to the annual defense spending of small nations. Cost overruns became a defining feature of the program, driven by immature technologies, integration challenges, and changing requirements. The scale of the ship itself reflects this investment. Displacing over 100,000 tons, the Ford class functions as a floating airbase, capable of carrying more than 70 aircraft and supporting thousands of personnel. Its flight deck, internal layout, and weapons elevators were redesigned to increase aircraft launch rates and reduce manpower requirements. In theory, these efficiencies would lower lifetime operating costs compared to the Nimitz class, though early service experience has complicated those assumptions. Operational challenges emerged quickly. Reliability issues with the launch and recovery systems delayed full operational capability, and early deployments were postponed while systems underwent refinement. Critics argued that the Navy had attempted to introduce too many unproven technologies at once, compounding risk and cost. Supporters countered that such risks were unavoidable if carrier aviation was to remain viable against future threats. Despite controversy, the Gerald R. Ford class remained central to U.S. naval strategy. Aircraft carriers continue to serve as symbols of power projection, deterrence, and global presence. No other platform combines mobility, endurance, and sustained air operations at comparable scale. The Ford class was not abandoned, but it demonstrated the upper financial limits of naval construction. Each ship represents a national-level investment, forcing difficult trade-offs between innovation, affordability, and fleet size. It stands as a reminder that in modern warfare, technological superiority often carries a price measured not in millions, but in national budgets. The Space Shuttle program, reusable spaceflight that cost more than Apollo. The Space Shuttle program was conceived as a revolutionary leap in spaceflight, promising routine, reusable access to orbit that would dramatically reduce costs and expand human activity in space. Its origins date to the early 1970s, when NASA sought a post-Apollo mission that would preserve funding, retain industrial capacity, and maintain U.S. leadership in space. Approved in 1972, the shuttle was envisioned as a partially reusable spacecraft capable of launching satellites, conducting research, servicing space stations, and returning large payloads to Earth. The system that emerged was far more complex than originally advertised. Each space shuttle consisted of 3 major elements: the reusable orbiter, 2 solid rocket boosters, and a large external fuel tank. While the boosters were recovered and reused, and the orbiter was flown multiple times, the external tank was discarded after every launch. The shuttle first flew on April 12, 1981 with STS-1, inaugurating an era of reusable crewed spacecraft that lasted 3 decades. From a technical standpoint, the shuttle achieved remarkable feats. It deployed and repaired satellites, most famously servicing the Hubble Space Telescope, and enabled construction of the International Space Station. It carried astronauts, laboratories, and cargo unmatched by any other spacecraft. However, these achievements came at an extraordinary cost. Although marketed as a low-cost alternative to expendable rockets, the shuttle proved to be far more expensive to operate than initially predicted. Between 1972 and 2011, total program costs are estimated to have exceeded $200 billion when adjusted for inflation. This figure surpasses the entire Apollo program, which cost approximately $150 billion in today's terms and achieved the first human landings on the Moon. Each shuttle launch ultimately costs well over $1 billion, largely due to extensive refurbishment, labor-intensive inspections, and complex ground support infrastructure. The program also carried a significant risk. 2 catastrophic accidents, Challenger in 1986 and Columbia in 2003, killed 14 astronauts and exposed fundamental design vulnerabilities. Both disasters grounded the fleet for years, driving costs even higher and forcing redesigns. These events underscored that the shuttle was neither airline-like nor routine, but an experimental vehicle flown repeatedly under tight political and schedule pressure. As technology advanced, the shuttle's limitations became increasingly apparent. It was expensive, fragile, and ill-suited for deep space exploration beyond low Earth orbit. By the 2000s, newer expendable rockets could launch payloads more cheaply, while the shuttle's unique capabilities no longer justified its cost. The Space Shuttle program was retired in 2011, not because it failed to work, but because it failed to deliver on its economic promise. It stands as a paradox in space history, a reusable system that expanded human capability in orbit, yet ultimately cost more than the lunar program it was meant to replace. The F-35 Lightning II program, a fighter program more expensive than most nations. The F-35 Lightning II program is the most expensive weapons development effort in history, a multinational fighter project whose total cost exceeds the gross domestic product of many small countries. Its origins trace back to the early 1990s, when the United States sought a single aircraft to replace a wide range of aging platforms across the Air Force, Navy, and Marine Corps. Known initially as the Joint Strike Fighter program, the goal was to achieve cost savings through commonality while delivering advanced stealth, sensors, and multi-role capability. Lockheed Martin was selected as the prime contractor in 2001, defeating Boeing's X-32. The resulting aircraft family included 3 distinct variants: the F-35A for conventional Air Force operations, the F-35B with short takeoff and vertical landing capability for the Marine Corps, and the F-35C designed for aircraft carrier operations. While these variants shared a common design philosophy, the engineering compromises required to satisfy all 3 services introduced immense technical complexity. The financial scale of the program quickly became unprecedented. Development costs alone exceeded $55 billion, far above initial estimates. When procurement and projected operating costs over the aircraft's lifetime are included, total program costs are estimated at over $1.7 trillion. This figure rivals or surpasses the entire economic output of dozens of sovereign states. Annual spending on the F-35 program has, at times, exceeded the full defense budgets of smaller nations. Cost growth was driven by multiple factors. The program pursued aggressive concurrency, meaning aircraft were built and delivered before testing was complete, leading to expensive retrofits. Software development proved far more difficult than anticipated, with millions of lines of code required to integrate sensors, weapons, and mission systems. Early aircraft suffered from reliability issues, maintenance challenges, and performance shortfalls that required years of corrective work. Despite criticism, the F-35 is an exceptionally capable combat system. Its stealth design, sensor fusion, and networked warfare capabilities allow pilots to detect, track, and engage targets long before being seen. The aircraft serves not only as a fighter, but as an airborne intelligence and command node, sharing data across joint and allied forces. It has entered service with more than a dozen countries, reinforcing its role as a cornerstone of Western air power. Operational use has demonstrated both strengths and ongoing challenges. While the F-35 has achieved initial combat deployments and exercises worldwide, sustainment costs remain high, and readiness rates have drawn scrutiny. Maintenance requirements, spare parts availability, and software upgrades continue to demand significant investment. The F-35 program was never abandoned, but its sheer cost reshaped defense planning globally. It became a case study in how ambition, joint requirements, and technological leaps can push a single program beyond traditional economic limits. The Lightning II is not just a fighter aircraft, but a national-scale industrial and financial commitment, one whose price places it firmly among the most expensive machines ever built. The Large Hadron Collider, the machine built to break the universe's secrets. The Large Hadron Collider, commonly known as the LHC, is the most powerful and expensive scientific instrument ever constructed, built to probe the fundamental structure of reality itself. Its origins date back to the 1980s, when physicists began planning a successor to earlier particle accelerators at the European Organization for Nuclear Research, known as CERN. The goal was to reach energy levels high enough to test the limits of the standard model of particle physics and explore phenomena that could not be observed anywhere else. Construction of the LHC officially began in 1998 near Geneva, Switzerland, using a 27-kilometer circular tunnel originally excavated for the Large Electron-Positron Collider. Rather than build a new tunnel, engineers repurposed existing infrastructure, though the complexity of the machine itself far exceeded anything that came before it. The collider accelerates protons to near the speed of light and smashes them together at energies measured in tera-electron volts, recreating conditions that existed fractions of a second after the Big Bang. The technical challenges were immense. The LHC relies on more than 1,200 superconducting dipole magnets, cooled to 1.9 Kelvin using liquid helium, making it colder than outer space. This cryogenic system is one of the largest and most complex ever built. The machine also includes massive particle detectors such as ATLAS and CMS, each the size of a multi-story building and weighing thousands of tons. These detectors record the debris from particle collisions, allowing scientists to reconstruct events occurring at subatomic scales. Financially, the LHC rivals the budgets of small nations. Construction costs alone exceeded 7.5 billion euros, with additional billions spent on detectors, upgrades, and long-term operations. Funding came from more than 20 member states, along with contributions from observer nations and international partners. For some participating countries, annual contributions represented a significant portion of their national science budgets. The collider became operational in 2008, though an early electrical failure delayed full operation. Its most famous achievement came in 2012 when CERN announced the discovery of the Higgs boson, confirming a key prediction of the Standard Model and earning the 2013 Nobel Prize in Physics for François Englert and Peter Higgs. This discovery justified decades of planning and unprecedented expense. Beyond the Higgs, the LHC continues to search for dark matter candidates, extra dimensions, and new fundamental forces. While it has not yet overturned existing theories, it has placed strict limits on what new physics can exist, reshaping scientific understanding through absence as much as discovery. The Large Hadron Collider is not a weapon, vehicle, or infrastructure project, yet it stands among the most costly machines ever built. It represents humanity's willingness to invest national-scale resources not for profit or power, but for knowledge. The LHC proves that breaking the universe's secrets sometimes requires machines as vast and expensive as the mysteries they are built to explore. The Manhattan Project infrastructure, the industrial system that built the atomic age. The Manhattan Project was not a single weapon or laboratory, but a vast, interconnected industrial system whose cost, scale, and secrecy rivaled that of a small nation. Initiated in 1942 during the Second World War, the project aimed to develop the world's first atomic weapons before Nazi Germany could do the same. Under the overall leadership of Major General Leslie Groves and scientific direction by physicist J. Robert Oppenheimer, the United States constructed an unprecedented network of facilities dedicated to nuclear research, material production, and weapon assembly. At its peak, the Manhattan Project employed more than 130,000 people across multiple secret cities and industrial sites, most of which did not exist before the war. The most critical installations were Oak Ridge, Tennessee, Hanford, Washington, and Los Alamos, New Mexico. Each served a specialized function within the atomic supply chain. Oak Ridge focused on uranium enrichment, Hanford produced plutonium in large nuclear reactors, and Los Alamos handled weapon design, testing, and final assembly. The industrial effort at Oak Ridge alone rivaled the output of the major manufacturing centers. Multiple enrichment methods were pursued simultaneously, including electromagnetic separation at the Y-12 plant, gaseous diffusion at the K-25 facility, and thermal diffusion at S-50. These plants consumed enormous amounts of electricity, at times accounting for a significant portion of total U.S. power generation. Hanford, meanwhile, became home to the world's first large-scale plutonium production reactors, supported by chemical separation plants that processed intensely radioactive material under extreme conditions. Financially, the Manhattan Project was staggering for its time. Between 1942 to 1946, the program cost approximately $2 billion, equivalent to over $30 billion in modern terms. This made it one of the most expensive undertakings of the war, exceeding the costs of many major weapons programs and surpassing the annual budgets of numerous countries in the 1940s. The investment was made without public debate, concealed behind layers of classification and compartmentalization. The infrastructure was built at extraordinary speed. Entire cities appeared almost overnight, complete with housing, hospitals, schools, and transportation networks, all operating under strict security. Many workers were unaware of the project's true purpose, performing repetitive tasks without understanding their role in creating nuclear weapons. The logistical challenge of coordinating materials, personnel, and information across such a vast system was unprecedented. The Manhattan Project infrastructure achieved its goal in 1945, producing the atomic bombs dropped on Hiroshima and Nagasaki. Almost immediately afterward, parts of the system were dismantled, repurposed, or absorbed into the emerging U.S. nuclear establishment. Yet its legacy endured. The industrial model it created became the foundation of the nuclear weapons complex and the broader atomic age. The Manhattan Project was not just a scientific triumph, but a demonstration of how an entire industrial ecosystem could be mobilized at national scale. It stands as one of the most consequential and costly machines ever built, not in steel or concrete alone, but in factories, reactors, cities, and human effort. The James Webb Space Telescope, a telescope that cost more than entire space agencies. The James Webb Space Telescope, often called JWST, is the most expensive and complex space observatory ever built, with costs that surpass the entire annual budgets of many national space agencies. Its origins trace back to the mid-1990s, when NASA began planning a successor to the Hubble Space Telescope, capable of observing the universe in infrared wavelengths with far greater sensitivity. Initially envisioned as a relatively modest project known as the Next Generation Space Telescope, it gradually evolved into an engineering undertaking of unprecedented ambition. Formal development began in 2002, with NASA leading the program in partnership with the European Space Agency and the Canadian Space Agency. From the outset, JWST posed extraordinary technical challenges. Unlike Hubble, which orbits Earth, Webb was designed to operate at the second Lagrange point, approximately 1.5 million kilometers from Earth. This location provides a stable thermal environment, but makes servicing impossible. Every component therefore had to work perfectly the first time, driving complexity, testing requirements, and cost upward. The telescope's defining feature is its 6.5-meter primary mirror, composed of 18 hexagonal segments made from beryllium and coated in gold to optimize infrared reflection. When combined, the mirror provides more than 6 times the light collecting area of Hubble. To keep the instruments cold enough to detect faint infrared signals, JWST uses a tennis court-sized sunshield made of 5 ultra-thin layers of Kapton. This sunshield had to be folded precisely to fit inside a launch vehicle and then deployed flawlessly in space through a series of complex mechanical steps. Financially, JWST became a cautionary tale in large-scale science management. Early estimates placed total costs at around $1 billion. As technical difficulties mounted, that figure rose dramatically. By the time of launch, the program's total life cycle cost exceeded $10 billion, including development, launch, and operations. This sum exceeded the annual space budgets of most countries and forced NASA to delay or cancel other scientific missions to keep Webb alive. After years of delays, the telescope was launched on the 25th of December 2021 aboard an Ariane 5 rocket from French Guiana. Over the following month, JWST successfully completed a complex sequence of deployments, including mirror alignment and sunshield extension, a process many engineers had described as the most dangerous phase of the mission. By mid-2022, the telescope began returning images that exceeded expectations, revealing unprecedented detail in distant galaxies, star-forming regions, and exoplanet atmospheres. Scientifically, Webb has already transformed astronomy, validating the enormous investment. Yet its cost remains central to its legacy. The James Webb Space Telescope stands as proof that answering the deepest questions about the universe can demand resources on a national scale. It is a single machine whose price equaled that of entire space programs, built on the belief that some discoveries are worth almost any cost. The Three Gorges Dam, the largest power machine ever built by humanity. The Three Gorges Dam is the largest power-generating machine ever constructed, representing one of the most expensive and ambitious infrastructure projects in human history. Built across the Yangtze River in Hubei Province, China, the dam was conceived as both an energy solution and a national development project. Serious planning began in the 1950s, but political instability delayed execution until the late 20th century. Construction officially started in 1994, and the project reached full operational status in 2012. The scale of the Three Gorges Dam is unparalleled. The structure stretches approximately 2,335 meters across the river and rises 185 meters above its foundation. It created a reservoir extending more than 600 kilometers upstream, permanently altering one of the world's great river systems. At full capacity, the dam houses 32 main turbine generators, each rated at 700 megawatts, along with 2 smaller auxiliary units. This gives the facility a total installed capacity of 22,500 megawatts, making it the most powerful hydroelectric plant ever built. Financially, the dam dwarfed most national infrastructure projects. Official Chinese government figures place the total cost at around 203 billion yuan, equivalent to roughly 30 to 35 billion US dollars at the time of completion. Independent estimates suggest the true cost may have been significantly higher when accounting for resettlement, environmental mitigation, and long-term maintenance. At its peak, annual spending on the project exceeded the total infrastructure budgets of several small countries, making it a machine funded at near-national economic scale. Beyond power generation, the dam was designed to serve multiple strategic purposes. Flood control was a primary justification, as the Yangtze River had historically caused devastating floods, resulting in millions of deaths. The dam was also intended to improve inland navigation by allowing larger ships to travel upriver through a system of locks and a ship lift. These benefits were presented as justification for the project's enormous cost and social impact. That impact was profound. Construction of the reservoir required the relocation of more than 1.3 million people and the flooding of hundreds of towns, villages, and archaeological sites. Environmental consequences included habitat loss, increased landslide risk, sediment buildup, and changes to river ecology. Critics argued that the long-term costs, both human and environmental, were underestimated during planning. Despite controversy, the Three Gorges Dam has delivered unprecedented electrical output, generating over 100 terawatt-hours annually in strong water years. It plays a central role in China's energy grid, reducing reliance on coal and supporting industrial growth across multiple provinces. The Three Gorges Dam was not abandoned or downsized, but its sheer cost and impact ensure it will never be repeated. It stands as a machine built on the scale of civilization itself, demonstrating that humanity is capable of reshaping entire landscapes in pursuit of power, stability, and national ambition. The Channel Tunnel, the underground machine that bankrupted investors. The Channel Tunnel, commonly known as the Channel, is one of the most ambitious civil engineering projects ever completed and a striking example of how megastructures can overwhelm even optimistic financial models. Conceived as a permanent rail link between the United Kingdom and France, the tunnel was intended to symbolize European integration while transforming trade and travel. Although proposals for a cross-channel tunnel date back to the 19th century, the modern project only became viable in the late 20th century due to advances in tunneling technology and political support on both sides. Formal approval was granted in 1986 when British and French governments signed the Treaty of Canterbury. Uniquely, the project was structured to receive no direct public funding. Instead, it was financed entirely through private capital raised by Eurotunnel, a binational company responsible for construction and operation. This decision transferred financial risk almost entirely to investors, setting the stage for future collapse. Construction began in 1988 and required the coordination of thousands of workers and massive industrial equipment. The tunnel itself is a complex system rather than a single passage. It consists of 3 parallel tunnels, 2 rail tunnels carrying traffic in opposite directions, and a smaller service tunnel used for maintenance and emergency access. The total length is approximately 50.45 kilometers, with about 37.9 kilometers running beneath the seabed, making it the longest undersea tunnel in the world. 11 tunnel boring machines operated simultaneously from both the British and French sides, cutting through chalk marl beneath the English Channel with millimeter-level precision. From an engineering perspective, the project was a success. The tunnels met beneath the sea in 1990 with remarkable accuracy, and the system incorporated advanced ventilation, fire safety, and drainage infrastructure. However, the financial assumptions underpinning the project proved deeply flawed. Construction costs escalated dramatically due to design changes, delays, and unforeseen technical challenges. Initial estimates of around £5 billion ballooned to more than £9 billion by completion. The Channel Tunnel officially opened in 1994, but revenue fell far short of projections. Passenger numbers and freight traffic were lower than expected, while interest payments on enormous debt consumed operating income. Competition from ferries and later low-cost airlines further eroded profitability. By the late 1990s, Eurotunnel was struggling under a debt load that exceeded £8 billion. The financial crisis culminated in 2006, when Eurotunnel effectively entered bankruptcy protection and underwent a major debt restructuring. Shareholders were largely wiped out, while creditors absorbed losses to keep the tunnel operating. Although the infrastructure itself continued to function reliably, it had already destroyed billions in private investment. Today, the Channel Tunnel is an essential piece of European transport infrastructure, carrying millions of passengers and significant freight volumes each year. Yet its legacy is cautionary. The tunnel proved that even a technically successful mega machine can fail financially on a national scale. It stands as a reminder that engineering triumph does not guarantee economic sustainability, and that ambition alone cannot overcome the unforgiving mathematics of debt and demand. The Soviet Energia-Buran program, a space system that bankrupted an empire. The Soviet Energia-Buran program was the most ambitious and expensive space effort ever undertaken by the USSR, conceived during the late Cold War as a direct response to the American space shuttle. Its origins trace to the mid-1970s, when Soviet leadership concluded that the shuttle might possess military capabilities threatening strategic balance. In 1976, the Council of Ministers formally approved development of a reusable spaceplane paired with a new heavy-lift launch vehicle, assigning overall responsibility to the Energia Design Bureau under chief designer Valentin Glushko. Unlike its American counterpart, the Soviet system was divided into 2 distinct elements. Energia was a super-heavy launch vehicle designed to loft extremely large payloads into orbit, while Buran was a reusable orbiter intended for crewed and uncrewed missions. Energia itself was among the most powerful rockets ever built, using a core stage powered by 4 ARD-0120 hydrogen engines and 4 strap-on boosters derived from the Zenit rocket. In theory, Energia could lift more than 100 metric tons to low Earth orbit, exceeding the shuttle's capability. The Buran orbiter resembled the American shuttle in outward appearance, but differed significantly in design philosophy. It lacked main engines, relying entirely on Energia for launch, and featured more advanced automated flight control systems. This emphasis on automation culminated on November 15, 1988, when Buran completed its first and only orbital mission. The spacecraft flew 2 orbits around Earth and landed autonomously at Baikonur Cosmodrome, a technical achievement unmatched by any crewed spaceplane at the time. Technically, the program was a success. Politically and economically, it was catastrophic. Development required the construction of new launch complexes, manufacturing plants, transportation infrastructure, and entire support industries. At its peak, the program involved hundreds of thousands of workers across the Soviet Union. Precise cost figures remain classified or disputed, but estimates suggest the program consumed tens of billions of rubles, representing an enormous share of the Soviet aerospace budget during the 1980s. The strategic justification for Energia-Buran collapsed rapidly. The Buran orbiter never carried a crew, never deployed payloads operationally, and never flew again. Meanwhile, the Soviet economy was already under severe strain from stagnation, military spending, and systemic inefficiencies. By the late 1980s, funding became inconsistent, schedules slipped, and political support evaporated. Following the dissolution of the Soviet Union in 1991, the program effectively died. In 1993, the Russian government formally canceled Energia-Buran. Facilities were abandoned, hardware was scrapped, and the surviving Buran orbiter was left in storage. In 2002, it was destroyed when the roof of its hangar at Baikonur collapsed. The Energia-Buran program was not abandoned because it failed technologically, but because it succeeded at a cost the Soviet system could not sustain. It stands as a symbol of late Cold War excess, where national prestige and strategic fear drove investment beyond economic reality. In the end, the space system did not merely outlive its purpose, it outspent the empire that built it. The Nimitz-class aircraft carrier, the floating cities that redefined naval cost. The Nimitz-class aircraft carriers redefined the financial and industrial scale of modern naval warfare, becoming some of the most expensive and complex machines ever built. Conceived during the late 1960s, the class emerged from U.S. Navy efforts to extend nuclear propulsion from submarines to surface combatants capable of sustaining global power projection. The lead ship, USS Nimitz, CVN-68, was laid down in 1968 and commissioned in 1975, marking the beginning of a carrier lineage that would dominate naval strategy for decades. Each Nimitz-class carrier functions less like a ship and more like a floating city, displacing over 100,000 tons at full load and measuring more than 330 meters in length. These vessels carry air wings of 60 to 70 aircraft and crews, exceeding 5,000 personnel when embarked. Power is provided by two A4W nuclear reactors, allowing operational endurance measured in decades rather than months. Refueling occurs roughly once every 25 years, a capability that fundamentally altered carrier deployment patterns and logistical planning. The financial implications of this scale were unprecedented. Construction costs for early Nimitz-class ships were already several billion US dollars each, and later units grew progressively more expensive due to inflation, technological upgrades, and increased labor costs. When accounting for life cycle expenses, including refueling overhauls, maintenance, modernization, air wing support, and personnel, the total cost of a single Nimitz-class carrier is estimated to exceed $20 billion. Operating one ship annually requires budgets comparable to the defense spending of smaller nations. Technological sophistication drove much of this cost. Nimitz-class carriers incorporated advanced radar systems, electronic warfare suites, and layered defensive weapons, evolving continuously throughout their service lives. The flight deck alone operates as an industrial machine, coordinating catapults, arresting gear, aircraft elevators, and fueling systems under intense operational tempo. Every subsystem required redundancy, survivability, and integration at a scale unmatched by any other naval platform. Despite their expense, the Nimitz class proved strategically indispensable. These carriers formed the backbone of U.S. naval power projection during the late Cold War and post-Cold War eras, participating in conflicts from the Persian Gulf to Afghanistan. Their ability to sustain air operations without reliance on foreign bases provided political flexibility and rapid response capability unmatched by land-based forces. However, their success also locked the Navy into a cost structure that could not easily be reduced. Each carrier demanded a massive escort fleet, specialized shipyards, and nuclear-trained crews. As defense budgets tightened, the financial burden of maintaining multiple Nimitz-class carriers forced difficult trade-offs elsewhere in the fleet. The Nimitz class was not abandoned, but it permanently reset expectations for what a capital ship would cost. These floating cities demonstrated that modern naval dominance came with national-scale financial commitments. They remain a benchmark against which all future carrier programs are measured, not only in capability but in cost. ITER fusion reactor, the experimental star that consumes national budgets. ITER, the International Thermonuclear Experimental Reactor, is one of the most expensive and ambitious scientific machines ever attempted, designed to demonstrate whether nuclear fusion can be harnessed as a practical source of energy. The project originated during the Cold War in the mid-1980s, when the United States and the Soviet Union began discussing joint fusion research as a symbol of scientific cooperation. Formal agreements were signed in 2006, creating a multinational partnership that includes the European Union, United States, Russia, China, India, Japan, and South Korea. The reactor is being constructed at Saint-Paul-les-Durance in southern France and is based on a tokamak design which uses powerful magnetic fields to confine superheated plasma in a toroidal chamber. ITER is not intended to produce electricity for the grid. Its purpose is experimental, to demonstrate a sustained fusion reaction that produces significantly more energy than it consumes. The target is a fusion power output of 500 megawatts from an input of 50 megawatts, a tenfold energy gain never before achieved. The physical scale of ITER is enormous. The central tokamak will weigh more than 23,000 metric tons, with the entire complex exceeding 400,000 tons of concrete and steel. The vacuum vessel alone consists of 9 massive sectors, each weighing hundreds of tons and requiring millimeter-level precision during assembly. Surrounding the plasma chamber are superconducting magnets, some of the largest ever built, cooled to near absolute zero, while operating next to plasma temperatures exceeding 150 million degrees Celsius. Financially, ITER has become synonymous with cost escalation. Early estimates in the late 1990s placed total construction costs at around 5 billion euros. Over time, delays, design changes, inflation, and coordination challenges among international partners drove costs dramatically higher. Current estimates place total construction and operational costs well above 20 billion euros, with some analyses suggesting even higher long-term expenditures. For several participating nations, annual ITER contributions rival or exceed the budgets of their entire national energy research programs. The project's multinational structure added complexity. Instead of centralized procurement, many components are built by member countries and shipped to France for assembly. While politically appealing, this approach increased logistical risk, integration challenges, and delays. ITER has repeatedly missed milestone targets, with first plasma now scheduled for the mid-2020s and full deuterium-tritium operation planned for the 2030s. Critics argue that ITER consumes resources that could be spent on smaller, more flexible fusion approaches or renewable energy deployment. Supporters counter that no other project can answer the fundamental question ITER addresses: whether controlled fusion at reactor scale is physically achievable. Failure would be costly, but success would redefine global energy systems. ITER is not a power plant, weapon, or vehicle, but it is unquestionably a mega-machine. It represents humanity's attempt to build an artificial star on Earth, funded at national and multinational budgetary scale. Whether it becomes a breakthrough or a cautionary tale, ITER already stands as one of the most expensive experiments ever undertaken. The Large Synoptic Survey Telescope, Vera Rubin Observatory, a data machine with planetary scale ambition. The Large Synoptic Survey Telescope, now officially named the Vera C. Rubin Observatory, is one of the most ambitious data-generating machines ever built, designed to map the dynamic universe on an unprecedented scale. Its origins date to the early 2000s, when astronomers proposed a wide-field survey telescope capable of repeatedly imaging the entire visible southern sky. Unlike traditional observatories focused on narrow targets, this system was conceived as a continuous discovery engine, capturing change across time rather than isolated snapshots of space. Construction of the observatory began in the mid-2000s on Cerro Pachón in Chile, a site chosen for its altitude, dry climate, and excellent atmospheric conditions. At the heart of the facility is an 8.4-meter primary mirror, paired with a uniquely wide-field optical design that allows the telescope to image an area of sky roughly 40 times the size of the full moon in a single exposure. This combination makes the Rubin Observatory unmatched in its ability to to survey large portions of the sky rapidly and repeatedly. The most defining component of the system is its camera, the largest digital camera ever built for astronomy. Weighing over 3 metric tons and containing a 3.2 gigapixel sensor array, the camera captures images so large that a single photograph would require hundreds of ultra-high-definition screens to display at full resolution. Every few nights, the telescope will re-image the entire southern sky, creating a continuous record of cosmic motion and change. The financial scale of the project reflects its ambition. Construction costs exceeded $700 million, with total program costs including operations and data infrastructure approaching $1 billion. While smaller than some flagship space missions, the observatory's true expense lies in its data handling systems. Over its planned 10-year survey, known as the Legacy Survey of Space and Time, the Rubin Observatory is expected to generate tens of petabytes of data, rivaling the output of major global scientific facilities. Managing this data requires a distributed computing network spanning continents. Automated pipelines will process images in near real time, issuing alerts within minutes when transient events such as supernovae, near-Earth asteroids, or variable stars are detected. Millions of alerts per night will be distributed to scientists worldwide, fundamentally changing how astronomical research is conducted. The scientific goals are expansive. The observatory will map billions of galaxies to study dark matter and dark energy, catalog millions of asteroids to improve planetary defense, and create the most detailed time domain survey ever attempted. Rather than answering a single question, it is designed to enable discoveries not yet imagined. The Vera Rubin Observatory is not just a telescope, but a planetary-scale data machine. It represents a shift in science from observation to continuous monitoring, funded at national and international levels. Its success will be measured not in individual discoveries alone, but in how completely it transforms humanity's view of a changing universe.